Now what we want to do is we want to compute what T of alpha beta is. And here we got to remember what's my alpha. My alpha, I'm going to be doing one step at a time, 1, then 2, and then plugging it into my equation. Once I have it in my equation, I take the output and I represent it as a linear combination of these vectors. So we're going to be looking at what happens to T of 1, 1. Well, this is going to equal 3, 1 plus 1 plus 1 minus 1 x, which equals 6. And this is going to be a 1 plus x plus b 2 minus x. Which implies that 6 plus 0x is equal to a plus 2b plus a minus b all times x, which gives us the following system of equations. A plus 2b equals 6, and a minus b equals 0. And we can create an augmented matrix. 1, 2, 6, 1, minus 1, 0. Now we take R2 minus R1, replacing R2, gives us the system of equations 1, 2, 6, 0, minus 3, minus 6. We take R2, we multiply by 1 over minus 3. We plug back into R2, and we get 1, 2, 6, 0, 1, 2. And now we're going to take R1, subtract R2, and replace it into R1, and giving us, we're subtracting 2 R2s and putting it back into R1, giving us 1, 0, 2, 0, 1, 2. Well, this tells us that A equals 2 and B equals 2, which is really nice. And we're going to have to move all of this, all of this down. And we can see how these questions can slowly become longer, but the process is nothing we can't do. And it's nothing too complicated as long as we just follow the steps that we have. So now we're going to look at our second basic vector, which is 1, 2. We're going to look what happens to 1, 2 when we apply it to our equation. So we get 3, 1 plus 2 plus 1 minus 2 x, which equals 9 minus x. And we're setting this equal to a 1 plus x plus b 2 minus x. So 9 plus minus 1 times x is equal to a plus 2b plus a minus 1 or a minus b x, giving us the system of equations 2 or a plus 2b equals 9 and a minus b equals minus 1. And this is going to give us the following augmented matrix for this system of equations. 1, 2, 9, 1 minus 1 minus 1. R2 minus R1, replacing R2. It's going to give the matrix 1, 2, 9. 0 minus 3 minus 11, I want to say, minus 10. Here. And now we're going to take R3, R2, we're going to multiply by 1 over minus 3. We're going to put that back into R3, and we get 1, 2, 9, 0, 1, 10 over 3. And now we're going to take R1, subtract 2R2, put it back into R1, giving us 1, 0. And now 9 is the same thing as 27 over 3 minus 20 over 3 gives us 7 over 3, 0, 1, 10 over. So this gives me that A is equal to 7 over 3 and B is equal to 10 over 3. So now we have our two set of coordinates, which we can combine together. T, the matrix representation of T in alpha beta, is going to be equal to, well, our first column is 2, 2. And our second column is 7 over 3, 10 over 3. Now what we're going to do is we're going to compute what V of alpha is. And our V, remember, is 1, 3. And we want to know what 1, 3 equals in terms of A, B1, or A, 1, 1 plus B, 1, 2. And we showed in a previous video that this implies that A equals minus 1 and B equals 2. So this means that V alpha is equal to minus 1, 2. Now, what is T of 1, 3? T of 1, 3 is equal to 3 times 1 plus 3 times 1 plus 3 plus 1 minus 3x, which is equal to 12 minus 2x. And we want to verify now that T alpha beta times V alpha is equal to T of V represented using beta, or the coordinates of T and V using the basis beta. So first we're going to look at what is the the coordinates of T of 1, 3 using beta. So we have that 12 minus 2x equals looking at our system equations. We want this to be equal to A 1 plus x plus B 2 minus x. Remember, these vectors don't come from the matrix or the linear transformation, they come from our basis. So 1 plus x and 2 minus x is where I get these vectors from. And now rearranging, I get the system of, or we can create the system of equations. A plus 2b equals 12, and a minus b equals minus 2, giving us the augmented matrix 1, 2, 12, 1, minus 1, minus 2. Taking R2, subtracting R1, replacing R2, gives us the matrix 1, 2, 12, 1, minus 3, minus 14. Or, sorry, 0, minus 3, 14. Taking 1 over minus 1 over 3, R3, replacing R3 is going to give 1, 2, 12, 0, 1, 14 over 3. And now R1 minus 2, R2, replacing R1 is going to give 1, 0, 0, 1. And now 12 is 36 over 3 minus 2 of these is 28. So it's 36 minus 28, which will give me 8 over 3 and 14 over 3. So this tells me that we're equivalent to the system of equations A equaling 8 over 3 and B equaling 14 over 3. So here, my coordinates vector is going to be 8 over 3 and 14 over 3. Now I'm going to have, now I'm going to multiply T of alpha beta with the alpha to verify that they are in fact equal. And if we scroll up, we can see that we have the matrix 2, 2, 7 thirds, 10 thirds multiplied by the vector minus 1, 2. And we're just going to scroll up to show you that that is the vectors that we have, minus 1, 2, and 2, 2, 7 thirds, 10 thirds. 2, 2, 7 thirds, 10 thirds, minus 1, 2. And this is going to give us 2 times minus 1 plus 2 times 7 over 3, and 2 times minus 1 plus 2 times 10 over 3, which equals to 14 over 3 minus 6 over 3 gives us 8 over 3, and 20 over 3 minus 6 over 3 is 14 over 3. And lo and behold, they are. We can see that the process is getting harder because we're dealing with a more complicated linear transformation, but it's not harder in the sense of more difficult steps. It's the same process we've been doing this entire time. Set up your system of equations, solve, set up your system of equations, solve. Go through those motions. Do the first basis vector, second basis vector. What are your coefficients? That creates your matrix representation or your coordinates vector. The process for each of these pieces are the same, no matter what the linear transformation